Rational number.
In mathematics, a rational number is any number that can be expressed as the quotient or fraction pq of two integers, with the denominator q not equal to 0. Since q may be equal to 1, every integer is a rational number. The set of all rational numbers is usually denoted by a boldface q. It was thus named in 1895 by Peano after quotient, Italian for quotient. The decimal expansion of a rational number always either terminates after a finite number of digits or begins to repeat the same finite sequence of digits over and over. Moreover, any repeating or terminating decimal represents a rational number. These statements hold true not just for base 10, but also for binary, hexadecimal, or any other integer base. A real number that is not rational is called irrational. Irrational numbers include 2, p, e, and ph. The decimal expansion of an irrational number continues without repeating. Since the set of rational numbers is countable, and the set of real numbers is uncountable, almost all real numbers are irrational. The rational numbers can be formally defined as the equivalence classes of the quotient set, Zx, Z_0/, where the Cartesian product Zx, Z_0 is the set of all ordered pairs, m, n, where m and n are integers, n is not 0, n 0, and tilde is the equivalence relation defined by m1, n1, m2, n2, if, and only if, m1 n2. m2 n1 equals 0. In abstract algebra, the rational numbers together with certain operations of addition and multiplication form a field. This is the archetypical field of characteristic 0, and is the field of fractions for the ring of integers. Finite extensions of Q are called algebraic number fields, and the algebraic closure of Q is the field of algebraic numbers. In mathematical analysis, the rational numbers form a dense subset of the real numbers. The real numbers can be constructed from the rational numbers by completion, using Cauchy sequences, Dedekind cuts, or infinite decimals. 0 divided by any other integer equals 0, therefore 0 is a rational number, but division by 0 is undefined.
Terminology.
The term rational in reference to the set Q refers to the fact that a rational number represents a ratio of two integers. In mathematics, the adjective rational often means that the underlying field considered is the field Q of rational numbers. Rational polynomial usually, and most correctly, means a polynomial with rational coefficients, also called a polynomial over the rationals. However, rational function does not mean the underlying field is the rational numbers, and a rational algebraic curve is not an algebraic curve with rational coefficients.
Arithmetic. Embedding of integers.
Any integer n can be expressed as the rational number n/1.
Ordering.
Where both denominators are positive. If either denominator is negative, the fractions must first be converted into equivalent forms with positive denominators, through the equations. And
Addition.
Two fractions are added as follows.
Multiplication.
The rule for multiplication is
Division.
where c 0. Note that division is equivalent to multiplying by the reciprocal of the divisor fraction.
Inverse.
Additive and multiplicative inverses exist in the rational numbers.
Exponentiation to integer power.
If n is a non-negative integer, then and, if a 0.
Continued fraction representation.
A finite continued fraction is an expression such as where n are integers. Every rational number AB has two closely related expressions as a finite continued fraction, whose coefficients n can be determined by applying the Euclidean algorithm to a, b.
Formal construction.
Mathematically we may construct the rational numbers as equivalence classes of ordered pairs of integers, m, n, with n. 0. This space of equivalence classes is the quotient space, Zx, Z\0/, where m1, n1, m2, n2, if, and only if, m1 n2, m2 n1 equals 0. We can define addition and multiplication of these pairs with the following rules. And, if m2, 0, division by the equivalence relation, m1, n1, m2, n2, if, and only if, m1 n2, m2 n1 equals 0 is a congruence relation, that is it is compatible with the addition and multiplication defined above, and we may define Q to be the quotient set, Zx, Z\0/, that is we identified two pairs, m1, n1, and m2, n2, if they are equivalent in the above sense. This construction can be carried out in any integral domain, see field of fractions. We denote by the equivalence class containing m1, n1. If m1, n1, m2, n2, then, by definition, m1, n1, belongs to and m2, n2, belongs to. In this case we can write equals. Given any equivalence class there are a countably infinite number of representation, since the canonical choice for is chosen so that GCD, m, n, equals 1, that is m and n share no common factors, that is m and n are coprime. For example, we would write instead of or, even though equals equals. We can also define a total order on Q. Let be the n symbol and be the or symbol. We say that if the integers may be considered to be rational numbers by the embedding that maps M to
Properties.
the set Q, together with the addition and multiplication operations shown above, forms a field, the field of fractions of the integer z. The rationals are the smallest field with characteristic 0, every other field of characteristic 0 contains a copy of Q. The rational numbers are therefore the prime field for characteristic 0. The algebraic closure of Q, that is the field of roots of rational polynomials, is the algebraic numbers. The set of all rational numbers is countable. Since the set of all real numbers is uncountable, we say that almost all real numbers are irrational, in the sense of Lebesgue measure, that is the set of rational numbers is a null set. The rationals are a densely ordered set, between any two rationals, there sits another one, and, therefore, infinitely many other ones. For example, for any two fractions such that where are positive, we have any totally ordered set which is countable, dense, in the above sense, and has no least or greatest element is order isomorphic to the rational numbers.
Real numbers and topological properties.
The rationals are a dense subset of the real numbers, every real number has rational numbers arbitrarily close to it. A related property is that rational numbers are the only numbers with finite expansions as regular continued fractions. By virtue of their order, the rationals carry an order topology. The rational numbers, as a subspace of the real numbers, also carry a subspace topology. The rational numbers form a metric space by using the absolute difference metric d, x, y, equals x, y, and this yields a third topology on Q. All three topologies coincide and turn the rationals into a topological field. The rational numbers are an important example of a space which is not locally compact. The rationals are characterized topologically as the unique countable metrizable space without isolated points. The space is also totally disconnected. The rational numbers do not form a complete metric space. The real numbers are the completion of Q under the metric d, x, y, equals x, y, above.
P-adic numbers.
In addition to the absolute value metric mentioned above, there are other metrics which turn Q into a topological field. Let P be a prime number and for any non-zero integer, let AP equals P n, where Pn is the highest power of P dividing A. In addition set 0 P equals 0. For any rational number AB, we set ABP equals AP/BP. Then DP, X, Y, equals X. YP defines a metric on Q. The metric space, Q, DP, is not complete, and its completion is the p-adic number field QP. Ostrowski's theorem states that any non-trivial absolute value on the rational numbers Q is equivalent to either the usual real absolute value or a p-adic absolute value.